All right, welcome back, sports fans. Sorry, I always wanted to say that. But here we are again, still talking about active physics, now in sports chapter 2, what comes immediately after the first unit you taught, which was the home unit. We're going to attempt to cover a couple of the lessons here, 2.4 through 2.6 in this video. So moving right along here. The next activity, 2.4, called Defy Gravity. This is all about work, power, potential, and kinetic energy. Obviously, or hopefully, you know these concepts are all very related to one another. And students are going to learn about that relationship through an activity where they're measuring their jump, and be prepared to have on hand a scale in case they don't know their weight. They could take their weight in pounds and convert it into newtons, and have some meter sticks on hand for students to measure their jump height. So let's take a look at the pacing guide real quick here. And here we have Defy Gravity, it giving us 2.5. I do this in a little bit more, 2.5 and 0.5 for a 30-second version. I don't do this mini challenge thing right here. So feel free to take a full 3 periods or even longer with this one, as I'll talk about how there's quite a bit of formulas they'll be using. They'll need a lot of practice with that. But basically, they're going to do the activity period 1 and then period 2 direct instruction. I'll talk about some ways to do that. The reading is in the chapter, but what you can add to that reading for that second class. And then you have your energy practice problems, where they're going to need probably more than a class period to really get a handle on these problems. So let's go through a bit of this. So you do the activity, they take their data, do some calculations, and then you need to start basically getting this direct instruction on what is work, what is power. A couple things to watch out for. The typical assumption of what work is not true to physics. We see the formula for work, force, and it has to be applied over a distance. So this strong man just holding the weight is actually, though he may get tired, technically not doing work. So that's a misconception to watch out for with students, and some examples you may want to illustrate that, the difference in our physics definition versus what most people on the street would think of when they're doing work. Power rate at work's done. So, give them the notes, talk about, discuss it. And I like to supplement here with some labs where they find the amount of work they do climbing stairs or lifting weights. And if you Google this, there's some great labs out there already set up for you to carry out and guide students through calculating the work and power of going upstairs or lifting a weight. And I do that, and the students really like these labs. So I recommend, taking an extra day to go through this to reinforce these concepts and give them a little practice with using the formulas, because they will have to calculate the work and power when they do that. And some direct instruction on what is potential and kinetic energy, because as you lift something, as you do work, you're storing energy, potential energy, energy stored due to position. I like to demonstrate this by lifting a book and talk about doing work to the book. And the higher I lift it, the more potential energy I'd give. And I drop the book from different heights, and they can hear the difference in sound as it hits, and talk about storing more energy as I lift it higher, and I can relate that to the formula. Or even the mass, a larger book versus a smaller book. So very easy, simple demonstrations, or even energy stored in an elastic band, potential energy due to stretching out that elastic band and letting go as it turns into kinetic energy. So remember, we talked about kinetic energy in the home unit when we talked about the movement of the molecules. When we're measuring temperature, we're measuring the average kinetic energy. As it gets hotter, they move faster. So hopefully students start to remember kinetic energy as moving energy. Okay, some great things you could do around the kinetic and potential energy and the conversion of energy and the conservation of energy. PhET, I talked about this resource before. They have a wonderful skateboard lab which breaks down the energy. Go look on the PhET site, and some teachers put up some great lessons around this. So if you could get a hold of some computers and do this with your students. Roller coasters are great examples of this energy concepts here. Here's a link to a nice little roller coaster activity where they build it out of very simple materials you can get, and pipe insulation, very cheap, and using marbles. And Teach Engineering, the site has another one, or just Google, and you'll get a ton of different activities around that. So I like to supplement that. And here we go. This is where students are going to have most of the trouble. They need to practice using these formulas. Work and power, not too bad. Some things to look out for, though, when they start using potential kinetic energy formulas. Students sometimes forget the fact that gravity is needed to find potential energy. They'll usually be given in the problem the mass and the height. They'll multiply the two, think they're done. And you have to remind them, don't forget gravity's in there. And they can use 10. They can round 9.8 to 10. So that's fine. Kinetic energy. This, ninth graders have some difficulty with this. It doesn't look that complicated. Square the velocity, take half the mass, but multiply it together. But you might have to go step by step a few of these problems to show students how to manipulate this formula, how to actually compute this formula, okay? So just something to look out for there. This is a good time to get some copies of the MCAS formula sheet in front of your students. It has all these formulas they're going to be using, and have them use this and have this in front of them, looking up the formulas, and just get used to seeing this and how to use it. So now's a good time, since they're going to be using 4 formulas and they already used the heat formula earlier. So you could introduce that. All right, moving on, 2.5, the run and jump. This is all about the third law of motion, as well as drawing free body diagrams. Okay, they want you to, if we look at that, talk about the third law, and also, do a bit about free body diagrams. So we'll talk about how we do that here. Starting off the skateboard demo. Hopefully you have a skateboard or a wheelchair, something wheels on it. You could have students push and see how they move, and talk about the equal yet opposite force, or even just push on a wall or have them hit on their desk and talk about when they put a force down, they will feel a force the opposite direction up on their hand. And I like to supplement this a little bit. There's some creative ways. You could look up balloon racers. This is a fun one if you have time on your hands to do that, or a more simple one where they make a balloon racer using the straw tape on a string and they race it across the room. And just talking about action and reaction forces and how that powers the balloon racer, the balloon across. And of course, the physics classroom has a lot about the third law. That resource I talk a lot about. Check it out. All right. So, go through it and then supplement it with one of these activities. And then for the net force, this may be a whole nother day you might want to add on to that lesson. I like to start with the tug of war and talk about, how we find the net force, if the forces are going opposite versus the same way. And students love the tug of war demonstration at the beginning of class. And then there's a really nice activity, if you go to this link right here at the bottom, where students are actually going to match descriptions with free body diagrams, okay? So they need to know how to draw forces and what force diagrams look like. So this is a great matching activity, a good introduction to free body diagrams. So that works well with students. Check that link out. And then we're going to do some more free body activities in the next lesson, 2.6, mu of the shoe. I actually don't find the mu of the shoe when I do this. I actually focus, instead of using that formula to find the coefficient of friction, I actually focus on the things they're really going to need to know for the test, for the MCAS, and what the standards address, which is the difference between static and kinetic or slide-in friction, what affects the force of friction, mass, and the surface. So I actually have them, as they pull the shoe, try it on 2 different surfaces and pay special attention to the force right before it moves, which would be the static friction, and as it's sliding across at a constant velocity, the kinetic friction. And they should notice it is greater right before it moves. That force of static friction is greater. There's always questions about this on the MCAS. I don't know why they care so much about that, but they do. So what is friction? The force that opposes motion. Talk about that, and then have them draw that free body diagram after they do the activity. Here's an example of one, and leading students to show all the forces, how you draw them as arrows, vectors, introduce that concept of a vector, a magnitude with a direction, talk about that with students. And one thing I should note, we're using the word velocity, which they're